Terms and definitions. First, we go through the general terms and definitions as per ASME 5, 2019. The area of interest is a specific portion of object that's to be evaluated. So practically the area of interest is what you are checking from that component or the actual component. A defect is a flaw or a discontinuity whose shape, size, orientation, location, or properties not meet the specified acceptance criteria. So if a discontinuity is over and above the acceptance criteria, it's called a defect. The defect is always a discontinuity. Well, let's put it this way. The discontinuity turns into a defect if the size or the shape of it or the type of the discontinuity is not accepted according to acceptance criteria. And so the discontinuity is lack of continuity and indication that you receive or response you receive or what you observe that is not normal, and that need to be evaluated whether it is relevant discontinuity or non-relevant discontinuity. What is it is inherent, it was intentionally put there, say two part of the metal were fit up and you can see a line between the fit up, so that line is inherent there, that's intentionally put there, so that's a non-relevant discontinuity. That's not intentional. Evaluation is determination of whether a relevant indication is acceptable or not. So when you look at an indication or a flaw or a discontinuity, first you need to find out what it is. I mean, shape-wise, size-wise, type-wise, what was the reason for that? And that's called interpretation. So once you size the flaw, then you need to find out whether that particular discontinuity is acceptable or not. And this process, to compare it with the acceptance criteria and accept or reject it, called evaluation. And the sizing of the flaw, measuring the flaw, that's interpretation. Examination is exclusively for non-destructive examination within the context of ASME Section 5, and it's a process of determining the condition of a component or the area of a component. And false indication is an indication that is interpreted to be caused by a condition other than a discontinuity or imperfection. For example, there was a dirt there, or there was say the NDE was too sensitive and it took some spurious indication, some noises, which was not relevant, so that's called false indication. False indication also is a non-relevant indication. A flaw is an imperfection or discontinuity, which is detectable by non-destructive testing method you are using. And flaw characterization means to find the size, shape, orientation, location, and any other properties of that flaw based on the NDE examination, the response you get. And indication is the response or evidence from a non-destructive examination that you need to interpret. That means find out what it is, and in order to determine whether it's relevant or not. And inspection is actually the observation. So QC, normally term quality control, is actually doing the job. Inspection is observation that everything is in order, it's complying with the codes. And normally inspection is carried out by the client's rep or client's inspector. Interpretation is the process of determining whether an indication is non-relevant or relevant. And as we said, compare it with the and then trying to find out whether it is the size, the shape of it, and so that then once you know what it is, what is the size, where is it located, then you go for evaluation, which is comparing it with acceptance criteria and accept and reject. Limited certification, every NDT method, including UT, has got different techniques. For example, if somebody is only qualified to do lamination check with a 0-degree compression probe, so that's a limited certification in this sense, because he's only qualified to do 0-degree of compression with normal probe. He cannot do, he's not trained and qualified for angle beam or other NDE method. So that's called limited certification. Practically, a UT, in this case, it's got several techniques. So you are a level 2 UT or level 1 UT. If you know all the techniques, if you know just specific techniques, then that's limited certification that will be written in your certificate that you're only qualified to do that particular job. Method, there are 16 methods in NDE, such as radiography, RT, ultrasonic UT, magnetic particle NT, liquid penetrant PT or penetrant test, visual testing is VT, leak testing LT, and electromagnetic eddy current ET, and acoustic emission AE. That we brought some of the popular ones here. So these are the methods. Now, within the UT, there are different techniques that you do the job. So that's the difference between method and techniques. And non-destructive examination, as the name suggests, is non-destructive. It's an examination that's non-destructive, so it's not damaging the component while examining the material or component in order to find out the detect, locate, or measure, interpret, or evaluate flows, and hence non-destructive examination. This is versus destructive examination, a destructive test actually, such as tensile test, when you break a specimen to find its strength, its yield strength, ultimate strength, or a Sharpie test, where you break a specimen again to find out its toughness, or a bend test, when you bend the specimen to find its ductility. So this is the differentiation. And non-relevant indication is caused by a condition or type of discontinuity that's not rejectable. So false indication, for example, are non-relevant. And procedure actually tells you how to perform a job, or for example, UT procedure tells you how to do the UT, what is the scope, what is the purpose, what equipment to use, what sequence of actions you have to use, and how you're filling the report, and what's the qualification of personnel who do this job, etc. So it tells you the sequence of actions. That's the main part of a procedure. And procedure qualification, you have to somehow demonstrate that the procedure you have written and you are working according to is actually can detect the minimum required flow, or the type of the flow that you need to detect by that procedure. So you normally, in order to demonstrate that, you get a block with a known defect in it. For example, we got V1, V2 block with drilled holes in it, and if you can detect those holes, then that means first you calibrate your instrument at the same time, and also demonstrate that actually this procedure is working and you can detect the flow or discontinuity. Yeah. Reference standard is the construction code. For example, ASME section 8 for construction code for pressure vessel, or ASME B31.3 construction code for piping, and it tells what is a qualification of NDE personnel should be, Obviously, it refers to SNTTC1A, and as the qualification, and also it tells you, most importantly, the acceptance criteria. So the acceptance criteria is not in ASME Section 5. ASME Section 5 is simply tells you how to do the non-destructive examination, but it doesn't tell you what's the acceptance criteria. It's always referred to the construction code or reference standard. Now let's look at some particular terms and definition for ultrasonic examination. Amplitude, as you can see here, is the vertical pulse or height of a signal here, and each two peak or each two trough is one wavelength, and the velocity of sound is actually made of the wavelength divided by the time the number of frequency it passes. We'll talk about frequency later on, but this is the amplitude. This is the frequency of the sound, and the wavelength is between two peaks, can be distinguished as peaks. Angle beam, it's a probe that is directed at the angle, so the wedge actually designed so that when you put the probe on the wedge, the probe is at an angle, hits the material. In this case, this angle could be 45 degree, 60 degree, or 70 degree. And obviously, if it is 70 degree, then you can be closer to the location because this angle is increased. If it's 45 degree, you have to go back, so you hit this indication. So the sound path goes this way, and this is the angle which we call the angle of the probe, and this is a surface distance. And as the angle increased, the surface distance also is increased. A-scan, a method of data presentation utilizing a horizontal baseline. As you can see, this is the baseline here that indicates distance. So this is distance or time, and a vertical deflection from the baseline which indicates amplitude. So this is amplitude, and this is the distance or time. So when the sound hits, the first reflection is a primary reflection, and as you can see here, it hits at it keeps hitting the object at equal time interval, and you can see back reflection here. And then if you come here, you can see that you got some indications here, and then you got other. So this might be some porosity of that. And from the distance from the primary indication to the that one would be the depth, or the shape of this would indicate what type of discontinuity it is. It actually tells you, also gives you this new UT machines give you some number also here, so you know exactly what the distance is and what's the length of the indication. So this length from here to here would be the length of that indication that you see. Attenuation, when the sounds go through a medium, obviously it gets weakened as it goes by, the ultrasound. So and it is measured by decibel per unit length. And as the sound goes, it gets attenuated until it dies, totally dies, depending on the depth. So then that's why you have to use with various wavelength and frequency. So if you've got a longer frequency, a longer wavelength, then the penetration is more, but then the resolution or the smallest defect you can measure becomes, the size becomes more. So it's not that sensitive. At the same time, if you use lower frequency, the resolution is more and you can detect the smaller discontinuities, but then the penetration is less. So there is always a trade-off here. So attenuation is measured by decibel per unit length, and we can use this phenomenon actually to sort of calibrate and find out the sensitivity of the UT. We will explain later on. An attenuator device for altering the amplitude of ultrasonic indication in known increments like 2 decibel, 3 decibel, 6 decibel, 12 decibel, usually in decibels. So that's called the attenuator. You step down or step up to see what is the effect of that. Axial direction, direction of sound beam parallel to the component, to the major axis. So that's axial is always to the major axis is axial, and perpendicular to that would be transverse direction, obviously. And back reflection, when a sound wave hits and comes back. So this is a single 0 degree or normal probe or compression probe, and you can see you get two responses here. So the first response is a reference line as an initial one, and the second response is you can see the same height but at a distance here. So by the time it goes and hits and come back, that's a back wall echo, back reflection. So this distance would be practically the distance of the thickness of the material. So you can determine the thickness of the material by very simply and very accurately by a 90 degree probe or compression probe. Now, if there is a defect in between, right, so some of the waves hits come back the back wall echo that you see same place here, but smaller. That's because it's been some of the sounds have been hit the defect which was in the middle and came back. So you don't have the full sound going up and down like the first picture. So in second picture, you still get a back wall echo. So you know that's the thickness of the material again, EP. Then you see a strong signal in the middle, and that is the one that's coming back from the defect. Say, for example, lamination. And this distance, the D, would be where the depth of that defect is located. And if you want to find the length of that defect, so you move the probe from one end where you get this picture, so it's not actually hitting the defect, you move it this way and bring it here, and then by the time you get this defect, until you get this defect and it's still back to this defect, so you're coming from this end to this end, left side to right side. So that would be the length of the defect, practically, that you are hitting. Back wall echo, again, same thing. It hits, go back. You got the initial pulse, you got defect echo, and you got a back wall echo here. And back wall signal. Oh, this is back wall echo or back wall signal. There's an angle probe, and it hits a defect and comes back and receive it here. So this is a back wall, and this is what actually hits the defect, and you can see the indication there on an angle beam. Baseline is actually this line. The time of flight, distance travel, horizontal, accuracy A scan, CRT display for no signal condition. So this is called baseline. This is called initial pulse, the first pulse you get, and this is the pulse you get from the flow. You can see here, depending on the distance from the probe from the center, and you know what is the angle it is hitting, and you can easily find out this where the depth of this defect is, right? So you always we will explain this. Half a skip is half a length is going, and full skip is hitting and going up. So that's a full skip, it's called. Beam spread, the divergence of ultrasonic beam. As you can see, beam diversion is half of beam spread through a medium. So this is how the ultrasonic beam diverges. It's like a torch light. So you can always sort of control that the angle it's hitting and this hitting. So that's called beam spread. And B scan, we'll explain. So if you're scanning from the side, the cross section is a B scan. The C scan is the plan view from the top, and the A scan is actually this is the A scan. So it's a very good representative of that. So A scan is a linear one, and as you are going through that, just through the thickness, the A scan. The B scan is cross section, and the C scan is the plan. Calibration. Now, obviously, every measuring instrument needs to be calibrated, and practically you're comparing the readings with a standard another instrument or a calibration block. And the best thing is to do with a calibration block. So a calibration block has known defect, known holes, drilled holes with the size, the diameter of the hole, the location, the depth of the hole, and with that known, you throw the sound beam towards that by a probe, place the probe on the calibration block, and then if you get correct reading, so you practically calibrated your instrument. For example, here, some blocks, they have 3 holes. So you hit the first hole, hit the second hole, and then go back and hit the third hole. And you know at what depth, diameter they are, and what response you get there. So you practically calibrate your instruments here. So what reading you are getting here. The conferential direction, as I said, is perpendicular to the component's major axis as against the axial direction. So on a cylindrical components, circumferential direction is perpendicular to the component's major axis. Contact testing. So as the name suggests, you put the probe directly on the test piece and you use a couplant, because the ultrasound beams get attenuated very fast if there is an air between the test piece and the probe. So you use a couplant to facilitate that, and a couplant is a substance used between the search unit and examination surface to permit or improve transmission of ultrasonic energy. It can be oil, grease, wax, anything, if allowed. CRT is a cathode ray tube. It's practically a display, and C-scan is a plan view, as we explained pictorially up there of the test piece. Damping search unit, limiting the duration of a signal from a search unit subject to a pulse input, because this if you keep hitting that, you get a lot of signals continuously sending somewhere. So you're sending one peak and then damping it, and then sending another peak sound wave and then damping it, so that you can have a better resolution. So practically by electrically or mechanically decreasing the amplitude of successive cycles. So a higher damped pulse have increased resolution and sensitivity, while a lower damped pulse have increased penetration power, because you're sending too many sound waves, so you are penetrating better. But then too much noise you are getting at the result, and you need to sort of distinguish between which pulse you get from and which is the initial pulse, which is the backvolling curve, what is coming from the defect. There would be too many signals. You don't want that, so that's why you damp it. Just set one peak damp it, and then you get increased resolution and sensitivity. And decibel is same thing as damping, is 20 times logarithm of the ratio of two ultrasonic signal amplitudes. So if you say decrease by 3 decibels, you should get half of the value. You just want to check that the soundness of your instruments. If you do 6 decibel, which is very famous and that's called 6 decibel technique, you get a quarter of that. So the 80% should come to 20% of the full screen height, the response you get, and so forth. So if you do 2 decibel, then it's 25% just, 25% damped. If it's 3 decibel, it's a 1/2 damp. And if 6 decibel, it's quarter damped. So normally we use at this range, 6 decibel or 2 decibel. Diffraction, when a wave front direction has been changed by an obstacle or an inhomogeneity in the medium other than by reflection or refraction. We'll discuss this later on. Distance amplitude curve, practically when you send the initial pulse, and then you send the second pulse, and then it gets attenuated, and then you send that's a back reflection of the third pulse. Like the pulse goes up, so that's the first indication you get. That's the second cycle, the third cycle, and fourth cycle. So as different distances, right? So there is attenuation of the sound, and it gets reduced. So that way you can create a distance amplitude curve by connecting this peak of these lines. And so that is useful to find the depth of the discontinuities. So the amplitude, it depends on the distance practically. A dual search unit, as you can see, this is a dual search unit. It both receives and transmits elements. Echo is an indication of reflected energy. So that's a back wall echo, for example. And frequency, we have explained effective ultrasonic wave frequency of the system, and pulse repetition, number of times per second, and electroacoustic search is excited by the pulse generator to produce a pulse of ultrasound energy. This is called also pulse repetition rate. So you send one pulse, and then seconds another pulse after certain time. So that's called pulse repetition rate. Okay, so it's a pulse duration by the time the pulse goes and then dies down, and then second pulse, second wave of the sound you're sending, ultrasound. Immersion testing, when you immerse it in normally water, this is for high frequency, because the more the frequency of the probe, the thinner it is. Like 25 megahertz frequency is very, very thin crystal or quartz, and you can't really use it any other method than immersion testing, because it can break very easily. So normally we use with the portable probes, we use 1 to 5 megahertz. And immersion testing, you can do A scan, C scan. So practically the probe is in the water, and the water works as a couplant, and the object is placed there. Now it's going to give you an excellent C scan and B scan, but the advantage is it's not portable, and it needs a lot of setup, and it's an expensive way of scanning. Indication, any response or marks you get from the presence of a reflector. Initial pulse, we already discussed this. So you get the first pulse, initial pulse, and then they got a pulse from in the middle from the flow, and then you got a back wall pulse. So part of this is back wall, when the whole thing goes back wall, and because part of it is reflected earlier, so this is in the middle, because this just go half of, say, or 1/3 of the depth, or 2/3 of the depth comes back when it hits the defect. So you see this pulse back pulse from the defect earlier in the middle, whereas the back surface reflection is the whole through the thickness and it takes more time, so you see it later on. So that's why this is the initial pulse to compare them with this with the flow detection and back one. And you see that this got attenuated because part of it was deflected by the flow. Interface is a boundary between two materials. Longitudinal wave, we have basically two types of wave. Longitudinal and shear wave. As you can see, longitudinal wave, it expands and contracts and along the direction that's traveling. So that's called longitudinal wave. Whereas shear wave is actually sinusoidal and it actually vibrates perpendicular to the direction of particle motion. When the sound goes through, is perpendicular to the direction of the wave propagation. So longitudinal is expands and contracts, or direction of particle motion is along the wave propagation, whereas in shear wave it is perpendicular to the direction of wave propagation. That's the main difference of longitudinal waves and shear waves. Loss of back reflection, so absence or significant reduction in the amplitude of indication from back surface of the part under examination. That can be because the back surface was very rough and it scattered, so you didn't get any backhaul echo when it hit the other end of the object. Manual ultrasonic examination, technique of ultrasonic examination performed with search units that are manipulated by hand without the aid of any mechanical guidance system. Practically doing it manual with hand and moving the probe, scanning. Noise, any undesired signal that tends to interfere with the reception, interpretation, or processing of the desired signal. That's why you dump it. You've got dumping unit, you reduce the decibel, so you just see those signals that you want to see. You don't see too many, spurious signals and noises. Piezoelectric element. So this is piezoelectric, as you can see here, the blue one. And then you got backing material here. Then you got the case and everything else, and then and the wear plate. So wear plate, the way that it actually protects the piezoelectric from being worn off, or so you put it there, and it's a good transmitter also of the sound. And then you can see that size of piezoelectric, there are wires that once you put electrical pulse, the piezoelectric start vibrating, and that vibration is in the form of ultrasound. It gets generated, right, and it goes through. So that's the whole point of so piezoelectric materials are, when you deform it, it produces electrical charge. On the other hand, when you apply electrical charge or connect it to a positive negative wire, it starts mechanical vibration, and that mechanical vibration produces ultrasound. So that's the basic of ultrasound. Primary reference response, so the ultrasonic response from the basic calibration reflector at the specified sound path distance. So this is adjusted to a specified percentage of full screen height, say 80%. Pulse is a short wave trainers. Mechanical vibration, so you just give a very short wave train. That means you don't keep energizing it continuously. You energize the piezoelectric just a split second, it gives the sound waves, and then in known time you send another pulse. So that's called pulse echo method. That's why the name comes from. An inspection method, the presence and position of reflector are indicated by each echo amplitude and time. So there is a clock there that inside the machine practically. It could be electric or mechanical clock that sort of at known interval they send a pulse. And that's why pulse echo method. You don't want to send continuously because it will interfere with themselves, and you see a lot of noise. And the reference block, they use both as a measurement scale or the means of providing ultrasonic reflection of known characteristic. So, for example, you know this is 0.25 millimeter. You put the probe here, and then you calibrate your on the monitor. You should see 25 millimeter. So what you see the back wall echo should be 25 millimeter, or actually technically 50 millimeter, because it goes twice through the thickness. It goes once, hit the back, and then come back. And then you adjust it to 0.25, adjust it to 0.70, 75, and 1 inch. And so now you have calibrated your distance or the baseline on your UT machine. Reflector, the interface at which an ultrasonic beam encounters the change in acoustic impedance, and at which at least part of energy is reflected. And refraction is when the sound hits from one medium and hits another medium. So whatever is refracted is the same angle as you can see here, and then there's a Snell's law, and then when it hits another medium, it changes its angle also if it passes through. So part of it is refracted with the same angle. That's the Snell's law, and whatever is going through the second medium, it goes at a different angle. And the Snell's law say that the velocity of sound changes on a ratio of sine of this angle, theta 1, to sine of theta 2. Reject, suppression, control or minimizing or eliminating low amplitude signal, so that large signal are emphasized. That's like reject it or suppress it or damp it. Resolution, the ability of ultrasonic equipment to give simultaneous separate indication from discontinuities, and having nearly the same range and lateral position with respect to the beam axis. So how you can resolve two defects or two indications from each other. And search unit is a probe, actually what they call an electroacoustic device to transmit or receive ultrasonic energy, or both of them. So it can be a dual search unit or a single search unit, which is one sends signal and one receive it. So one should be at one side of the well, the other one should be on the other side of the well. Now if you use a dual search, which is both receiving and transmitting, then you just need to scan from one side of the well to receive a signal. The device generally consists of obviously nameplate, which says what is it, which megahertz is it, what's the diameter, a connector case, backing, piezoelectric element inside it, wear face, which is the bottom of the plate, so to protect the piezoelectric wedge, which actually gives the angle of the beam. So we already give you a schematic of a probe just before. And sensitivity measure of the smallest ultrasonic signal that you can actually detect with ultrasonic system. And normally they say it's half a wavelength. That's the minimum you can. So if you have a smaller wavelength, that means higher frequency, you have more sensitivity here. But then the damping is more, as we said, and the penetrating power is less. Shear wave, we already explained this. Direction of particle motion perpendicular to the motion of the sound is shear, whereas direction of particle along the motion is longitude. And sweep is the uniform repeated movement of an electron beam across CRT. So you're sort of widening the response or closing the response or removing some of the response outside of the monitor to focus on a particular response. So that's called sweep. Through transmission technique, So test procedure in which the ultrasonic vibration are emitted by one search unit and received by another. So this is you need one transmitter and one receiver here. So if there is no defect, you see the backward echo here. The initial response and the backward echo would be same height. If you see a defect here, and from the tip of the defect until there's another tip, the beginning until the end, you'll see this response. And this distance would be the depth of the defect. And as you move along, say if you come up to this point, you'll see the defect. And after that, you'll see the normal, no defect. So that would be the length of the defect on your screen. Time of flight, this is very, very popular. This is a completely new certification called time of flight diffraction. And practically, that means the time it takes for a sound wave to travel from a transmitting transducer to a flow, and then to the receiving transducer. So you got two probes. This is dual through transmission. One receives one, and you can see there is a jig here where actually keep them at a constant distance, and then the weld would be in the middle here between these two probes, and it keeps sending and receiving, and you see here the display here. So there is a defect, you see the display here, because these are each of these probe has got 3-4 transmitter and 3-4 receiver this end. So you're practically scanning the whole area, and you can see here there is some disturbance, so you can see that there is a defect here. It's very effective, very fast, and extremely popular nowadays with the industry. You don't need to know much about, but you just know what is this. Transducer, again, electroacoustic device for converting electrical energy to acoustic. This is a real picture of that with the dimension and all that. You can see what is it, and this is practically the number the manufacturer has given it. So it's a probe actually, the transducer. Ultrasonic, obviously any sound above 20,000 hertz that's not detectable by human ear is called ultrasonic, because you cannot hear it, and hence the name. And wedge is, this is practically a wedge that protects the piezoelectric, and also position the angle, like it's at an angle, so position the angle of the probe, so you would have an angle beam as well. So that's called a wedge, to direct the ultrasonic energy in the material at an angle. That's what the wedge is for. Thank you.